So let's go ahead and get started. Again, my name is Mike DeLaCluse. I'm president of Lesman Instrument Company. I'd like to thank all of you for taking the time out of your busy schedules to join us today for our webinar on Steam Traps 101, the basic technology and applications. Today's presenter is Tim Gaynor. Tim's a regional sales manager for Richards Industries, which owns Bestobell Steam Traps, Jordan Valves, Marwin Valves, Hex Valves, Low Flow Valves, and SteriFlow. Tim has more than 18 years experience in the industry. 15 of those years are with Richards Industries. Because of the large number of attendees, again, I have put everybody on mute. So if you have a question, please type it into the chat tool so we can respond. With that, I'll turn it over to Tim.
Hi, everybody. Thank you for joining us. Thanks for the introduction, Mike. Hopefully, everyone's had a chance to get the idea of what we're trying to accomplish here. We're keeping things very simple, very basics. I believe the invite to attend was Steam Trap 101, and that's all we're looking to do. We're going to talk about why you use steam traps. We're going to talk about some of the very popular steam trap designs and the benefits of some of them, perhaps weaknesses of some of them. We'll talk a little bit about applications, and the idea here is to give you an overview. One of the premises of this whole program is there's not a single type of trap technology that is perfect for every application, and so that's why we're going to go through 3 or 4 of the more popular ones, and then with that knowledge you might be able to say, hey, this particular design is good for heat exchangers, or this particular design is good for steam mains, that type of thing, and let you make a better educated decision on applications, for example. But again, we'll start with the basics. Just want to go, oh boy, I'm trying to page down and already ran into a problem. Well, that's not good. Hang on one second here. We'll get this figured out. It worked earlier. Let's go next. We might have to do it manually that way. We'll see what happens. Basics of what is a steam trap. A self-actuated or automatic mechanical valve that opens in the presence of condensate and closes when steam is present. Very simply, we want to get the liquid out of the steam system, but we don't want to allow the actual steam out for reasons of efficiency and for reasons of cost. Looks like I'm going to have to do a manual. Sorry, everybody, but we'll get through it. Why are steam traps important? Obviously, you want to get any liquid out as quickly as possible because that's going to impact the amount of heat transfer that you might have, and also getting the liquid out of your pipes, your vessels, your heat exchangers will also help reduce any corrosion that the liquid might have or might cause within those systems. And then also, you want to eliminate air and other non-condensables. As all of you know, air is a wonderful insulator, but that will keep the steam from doing its job, whether, again, you're heating up a product or a food or even just a liquid in a heat exchanger. If you have air, that's going to insulate and block some of those efficiencies. And then, speaking of efficiency, just to improve your overall steam efficiency, again, we want to get the water out as quickly as possible. I like to use the example of a cooker, and if you were making soup in a vessel, a blanketed vessel, you'll have steam on the outside, and that's going to heat up the soup that's inside of the vessel. Well, if you have water in the bottom of that, or you have air in the top of that, you're not getting that steam up against the wall as much as you want, so you don't have the efficiencies that you're looking for. A good steam trap will discriminate between steam and condensate and only let the condensate out. Again, ideally you're trapping the steam, hence the name, within the vessel or heat exchanger. You'll drain heat exchangers better for uniform maximum output. Again, we're talking about efficiencies here. Not subcool the condensate excessively where it will affect corrosion or performance. And what we're talking about here is you're always going to have some condensate backing up in the system. You have to have water at the trap, and the trap will open or modulate and let that out. But you'll always have some condensate backed up, and you want to minimize that. If you back it up too far, again, using the soup as an example, you'll back it up into the jacket, and you won't get the thermal transfer that you're looking for. A good steam trap will also adjust to varying loads. For instance, during startup, if the soup is real cold, as the steam comes in there, it's going to condense very rapidly, so the initial load is going to be much higher than your running load. A good trap will adjust to that. A good trap will adjust to varying condensate pressures if necessary. And a good trap will also be freeze-proof if steam is turned off. And we'll elaborate on that a little bit later in the presentation. Next slide. There we go. To size a steam trap, you're going to look for a lot of the same things that you look for a valve or a regulator. Ideally, you're going to know the application, whether it's a main or a drip or a tracer or a process trap, because that might change your selection, the type of technology that you might use. You would ideally know the differential pressure across the trap, the inlet pressure versus the outlet pressure on the condensate return side. Ideally, you'll know the capacity, and two considerations here. Again, we mentioned earlier that your startup load's typically going to be a much higher amount of condensate, and then once the system's up to temperature, you're not going to generate as much condensate. So ideally, you'll know both your startup capacity requirements and the hot running load requirements, and that will let you size the trap so that you make sure you can meet the requirements for both. And then we want to know if the steam is superheated, because that, depending on the trap technology you're utilizing, that will have an impact on one, its longevity, but also its performance. Now, we also know that in a lot of applications, the steam system has been there for 30 years, or maybe it was designed for a given load when it was installed 30 years ago, but now you've added various, you've added more reactors or more cookers or more equipment, more heat exchangers to it, and you may not know that. We get that every day. So you look at the line sizes, you look at the known, and perhaps you pick a trap that has the maximum capacity, or you pick an orifice size that has the maximum capacity. So there are applications where there's some guesswork, but at least you know line size and you know pressures, and that will help steer you into choosing the right trap or orifice size. Not going to get into real deep detail on this particular chart. All I wanted to do is, again, emphasize there's a lot of different types of traps out there, a lot of them based on change of state, a lot of them are temperature sensing, and my broad point here is there's a lot of different ones out there, and again, you want to match up as best you can to the application. We're going to go through a couple of these technologies now, though. A very popular type is a float and thermostatic trap, also known as F&Ts for obvious reasons, but these work on two very simple principles. One, you have a float, kind of like the float in your toilet, and you see the blue condensate coming in, and that float does exactly what it implies, and that opens the orifice. So as the flow of condensate increases, it pushes the ball up higher and opens the orifice even more. At the same time, you can have gas or air coming into the system. You have a thermostatic element in the top of the steam trap that opens and closes based on temperature. So you move to here where steam is getting into the trap, that will heat up the element, and that will close off so that you're not venting steam through the steam trap. But at the same time, it will still continue to drain liquid that enters the trap. This is a modulating trap. It's always open unless, of course, the system shut down or the condensate flow stops. The ball will sit and then close off that orifice. But it's designed to modulate and get rid of your air, get rid of your non-condensables, and get rid of condensate. Some advantages: they continuously discharge. I mentioned that they are modulating. So they're good for applications where the rate of heat transfer is high. So you see these on a lot of heat exchangers, for example. They handle both light and heavy loads very well, so they will adjust to varying condensate loads. Pressure fluctuations don't really hurt them, and they do discharge air. And one thing I'll mention, what we're talking about here are some universals that are true of any given brand. So there's several different manufacturers of float and thermostatics, dozens and dozens of them. And what we're trying to do here is give you a broad base. This is true of the float thermostatics that we make, that any other company would make. Just trying to give you some generalizations that you can use. Disadvantages of float thermostatics. The float in particular can be prone to damage from water hammer. If a slug of water gets sent into there and hits that hard, it can damage the float, crack it, dent it, that type of thing. Not real suitable for corrosive condensate or superheated steam. We've seen applications where the ball will come back and it's been corroded, eaten away because of acidic elements within the condensate itself. It'll eat that ball and you get a little crack in there, and obviously then the ball will fill with liquid and won't lift anymore. They're susceptible to freezing, and the size of the orifices can be varied, so you need to know the pressure, and if pressures do change, then sometimes that requires a seat change. Moving on to another very popular and prevalent type of technology, inverted buckets. This particular one is an inline, and then I also have a side entry one here in another slide or two. But these work, very simple principle. Your steam or condensate comes in through, again, this is an inline, through here, and then condensate goes up and around the bucket and out the orifice. Okay, very, very simple. If steam comes in, then it will float this bucket, this inverted bucket, and lift it, and that will close off the trap. So steam comes in, lifts it up, and then it will slowly vent through here and condense, and then over time, when the steam condenses, the bucket will sink back down and condensate will flow through. So this is a cyclic type of trap. It goes on and off. Here's an inverted one doing the same thing, except the flow comes in from the side. Again, condensate up through there and out through the orifice. And then when steam comes in, comes up through the middle and then floats the bucket, lifts it up within the condensate, and closes off the valve to stop the flow. Very simple, very prevalent traps that you see in the marketplace. Some advantages. Good for high pressure, decent for superheated steam. Not too bad for water hammer. You can see that most of the cases they're are not the inline type, but coming in from the side. So if there is water hammer, you get a lot of that absorbed within the pipe or before it actually gets to the bucket and hinge assemblies. Very simple design, very rugged, and very, very low in terms of maintenance also. Some of the disadvantages. The small vent in the top discharges air slowly and is also prone to wear. You always need to have some water in the trap to form a seal, and I'm going to back up here. Whoops, my bad. You always have to have a little bit of water here in the bottom so that when the steam comes in, it hits that. There we go. You have some water in the bottom of the trap, so when steam comes in, it hits that water, and that will allow the bucket to float. This is often referred to as the prime within a bucket trap. So if you don't have water down here, the steam's just going to flow through and out. So the water actually forms that seal. There's two problems with that, though. One, you've got to remember to set the prime, as it's called. So if you get a new trap, you've got to prime it. And then the other problem, which is the bullet point here, is they're susceptible to freezing. So if you have these outside and they're on an application that maybe you shut down at times, for whatever reason, production shuts down, normal shutdown, planned outage, whatever it might be, that prime in there can freeze. And then that can crack the trap depending on the material that it's made out of. or over time it could even evaporate out of the system, and then you're stuck with a trap that doesn't work when you restart it. And then the last thing, these will actually waste or use some energy. And again, this is anybody that makes bucket traps. It's just part of how they operate. Again, I'll go back to the picture one more time here. There we go. Again, we mentioned that for this to close, it's open, you're flowing condensate out through the orifice. For it to close, steam has to enter the trap and float that bucket and close it. So a bucket trap will use some steam in order to operate. Again, anybody's, no matter what brand or anything like that, they use about 2 pounds per hour. So you think about that, over the course of a 24-hour day, you're using close to 50 pounds of steam if it's operating at peak efficiency. And that's an important consideration when you look at how many traps do I have, how often do they work, and how much steam am I using just to operate that trap. Moving on to another very prevalent technology, this is the disc trap. Very, very simple, one moving part, this disc up here. So this particular one is open. You have condensate flowing through, it goes up and under the disc and out of the trap. All right, very, very simple operation. This is an on-off or cyclic type of technology. When you have steam come into the trap, it goes through here and the velocity increases, and this causes the cap or the disc, excuse me, to come down and close off the trap. So you'll hear a kind of a noise as that closes. I need to get my arrow to come up again. Sorry. So then once it's shut, you have steam up above and steam below, and then as this condenses, the pressure up here will drop, and any condensate here will push that back up and begin the flow of condensate through the disc trap again. Some of the advantage of these, they can operate within their entire working range without adjustment or change of size. They're very rugged. They're compact, very lightweight, simple design, and very cost effective. They can be used on high pressure and superheated steam. Water, hammer, and vibration really don't have much of an impact on these traps. Typically they're stainless steel, so any corrosion issues are eliminated. They're unlikely to freeze. They typically don't hold any condensate in them, so even if you shut down a process that these are on and it's outdoors, usually will end up draining any water, or because it's stainless steel, you won't get cracking. Easy maintenance. There's really only one moving part that needs to be replaced, although what you may see at times, the disc will cause some wear on the orifice from cycling. You know, these will cycle sometimes a couple times a minute depending on the running load that it's seeing. But there are many manufacturers that make a replaceable orifice and disc, so there are ways to address that. And last point, inexpensive. I mean, a lot of people don't look at the steam system and the traps as a main concern, and so what we see a lot of is I just need a 2-inch trap and I want something that's inexpensive, and they are. Disadvantages of disc traps. They don't operate effectively on real low inlet pressures or high back pressures on the condensate side. When exposed to very low ambient temperatures or rain, the flash steam in the control chamber, or that little area above the disc, will condense more rapidly than normal and cause it to open and shut more quickly. In fact, probably a dozen years ago, I was out doing a steam survey, and to test traps at this one facility, one of the maintenance people would actually just drop some water on it to see if it would cycle. So just go out there. It was hot out, but he would just pour a little bit of water on the top of the trap, and just that little cooling would cause it to cycle. But that can be an issue if they're outside and you're in rain or something like that. You might be passing steam where you don't want to. They're noisy traps, and like we said on bucket, these will waste or use some energy. Going back up to the picture, again, these need some steam to pass through here and pull the disc down to close. So same scenario, you're going to use about 2 pounds an hour, assuming they're working at peak efficiency.
Hey,
another very prevalent type of technology is thermostatic or bimetal. And I've got pictures of 3 different types here. And the basic principle with these is you have 2 metals that are bonded together, and as the temperature increases, those metals will bend. Next slide is, whoops, sorry about that. In a plate one like we have on the left, these metals, as these expand, it will lift, it'll heat. You don't want steam going through there, so the heat will expand these bimetals and pull the plate up, pull this plug up and close that out. On the disc side that we're looking at here, you can see this is expanded and has pulled it closed. The elements expand and lift the stem to pull it closed. The delta one we're going to go into a little bit more detail because that uses temperature and pressure, but the same thing, the same principle is true. As this element heats up, it pulls up on the stem to modulate that particular trap. Advantages of a bimetal: small in size when you compare them to a bucket or an F&T, but large condensate discharge capacities. High startup capacities since the valve goes wide open when it's cold, again because that bimetal is temperature sensitive. Withstand water hammer, corrosion, and high pressures. Most, and this is something to look at if you're looking at a bimetal trap, most of the internals will be some form of stainless steel to avoid corrosion, but not everybody's is, so that's another key thing to look for. Work over a wide range of pressures. Internals can typically be replaced with the traps in line. Disadvantages of bimetals, because the temperature change is necessary, they don't respond quickly to changes in load or pressure. And if the trap charges against back pressure, the condensate must cool down even more than normal before the valve will open. In fact, with some bimetal manufacturers, if your back pressure is more than 20% of your inlet pressure, you should alert them prior to a purchase so that they can make adjustments to the bimetals. There is one design that uses both pressure and temperature. It is a bimetal type, and these are designed for modulating discharge. So what you have is temperature expands that bimetal to pull it closed, but the line pressure of the condensate pushes down through the orifice and opens the valve. And what they're trying to accomplish with this is keep the discharge close to the steam curve. You don't want to have a whole lot of subcooling, as we mentioned earlier in this, and you don't want to have an on-off because you can, run out to here and then up. You got to have a little steam pass through, and then it cools off, and then up. You don't want to have that type of a discharge characteristic. And you also want to make sure, no matter what type of trap you're using, if you're venting to air, a lot of times you see this on tracer applications, make sure you know the difference between blowing steam, where your trap's not working, or flash, where you've got a little bit dribbling out and maybe some just vapor, almost like leaving your hot water faucet on in your kitchen. You got a little bit dripping out and you got a little vapor coming off of it. Want to be able to distinguish between those two, again, if you're venting to atmosphere. The bimetal that operates on temperature and pressure, again, just showing you how that works. So the pressure goes down and pushes down on the orifice to open it. And it is a modulating trap, but it will close off if steam gets in there. That will actually expand this element far enough that it will close if it gets hot enough. And the idea here is, unlike the disc type or the bucket, you don't pass any steam with that type of design. So you get the modulation, but again, we don't want to pass any steam through a trap if possible, because even at 2 pounds an hour, you're going to use a lot of steam over the lifetime of that trap. One other benefit of this particular technology, the way it's designed, you can reduce some of the components. You always want to have a strainer. You want to have a strainer upstream, and you want to have a check valve downstream. And the way this works is you have the strainer on the inlet, and then the valve assembly in here is loose, so that if you get back pressure on it, it will push that plug up and close it also. I'm going to back up a little bit here so you can see that better. So if you get back pressure on this, it will push up on the plug and close it. So there's a couple of different trap technologies that do the same thing, where you get the benefit of a strainer and a check valve in line. And there's two broad points we want to make here. One, there are more than one component in a steam trap station, and that's worth mentioning is we'll get calls that, hey, you know, this trap keeps clogging. Well, do you have a strainer upstream? No, I don't. Well, there's maybe the cause of your issue. Or a lot of people, although it's not a proper piping practice, they'll have two condensate lines of different pressure going into the same return line. Well, one's going to slow down the flow through the other. If you have one draining at 10 psi and another at 20, you're going to have issues. And we'll hear, hey, we're getting backflow through a trap in a given application. Well, a check valve will help that, but again, that's a piping issue. You always want to have the same condensate pressures on your return lines. But again, the idea here is having all the components in there, and there are technologies out there that have all those components in one type of trap. And that's all that we wanted to cover. Again, just wanted to highlight some technologies and let you know the positives and the negatives, and maybe give you some things to consider when you're looking at steam traps. And again, what we see a lot of is the steam traps are back burner items. You know, they're second behind control valves and instruments and things like that. But where we get more attention now is from people that are looking at efficiencies within a plant, looking at energy use and things like that. And they look closely at, hey, which technologies use steam, which ones don't. And you look at total cost of ownership. Okay, maybe a float and thermostatic or a bimetal is more expensive than a disc trap, but I have a strainer, I have a check valve in there, so I don't have to buy or pipe in those components. Or, hey, I'm not using any steam when this particular trap modulates. So there's a lot of considerations, and we're just trying to give you some food for thought, as the cliche goes, and hope that you all are working at places that have trap programs, and you test your traps regularly. In a given plant, we've always found that between 20 and 25% of the installed steam traps are not operating correctly. And that's a huge consideration, and that's a huge energy loss. So they are important components, and we're glad that you took some time to let us tell you a little bit about what we have, and hopefully this has been helpful for you. And I want to thank everybody for tuning in with us.
Hey, Tim.
Yeah.
We've got a question for you.
Okay.
The inverted bucket technology, what do you consider as high pressure?
Good question. Well, there's. Give me 1 second here. It's a great question, actually. That's a very. I gave a very vague description of that. There are different ratings, and this is also vague, but even within our own line, there's a couple of different ratings. They're good, and I don't know the max off the top of my head, to be honest. And there's also, besides us, there's other manufacturers, and I don't know their max ratings either. So I apologize, I really don't have a clean answer for that one. Stump me on that one. I just don't know the max for our product on that particular one.
Sounds like it's dependent on each bucket trap, and you got to look it up depending on the bucket trap.
And there's stainless ones out there. You know, most of the buckets are an iron of some type, typically cast. But I've seen stainless buckets in smaller sizes, so those will have much higher pressure ratings than a larger one would.
Right. How can one test a trap that's online and in service?
There's two very prevalent technologies that people will use. One is temperature sensing, and the other is ultrasonic. And temperature sensing is just what you would think. You typically measure the temperature at the inlet of the trap, and then you measure the temperature at the outlet of the trap. And there should be, and this varies depending on the type of trap, whether it's cyclic, whether it's modulating, but there should be a decent temperature drop across there because you're only letting water out of the outlet side. If you find that most traps will fail open, so if you find the temperature at the inlet and the temperature at the outlet is the same, you're probably blowing steam. Ultrasonic uses sound, and this is very useful if you have a cyclic type, because you put it on the outlet side of the trap, and when it's closed there really shouldn't be a whole lot of ultrasonic noise being generated, and then it opens and you'll get a lot of noise, and then it shuts back off and you should be down to zero. And it's also useful, you can tell if you have leakage, because like I mentioned on the disc trap, they're loud and you might hear that sound as it opens and closes, but just because it's closed doesn't mean it's not leaking. So ultrasonic will let you detect flow that's going through there even when it's closed. An ultrasonic can be used on a modulating tube, and what you want to see on the outlet is some adjustment of that flow. So you'll see that the ultrasonic level's changing. There's several different ways, but those are the two that are most prevalent that you see out there. And if you can use both, that's even better. It can be difficult with a modulating trap to decide, hey, is that leakage or is it actually modulating? But those are the key technologies, and you have to have the trap operating in order to test it. And it's a good question, because we'll do surveys sometimes and people will start out with, hey, this whole part of the plant is turned off, so let's go over there and test them. Well, you've got to have some flow and some steam being generated and condensate being generated in order to do any testing.
Okay, thank you. How do you go about priming a trap?
Well, there's, depending on whether it's an inline or side entry, there can be a plug, or when you are installing it, just put water in it. Okay.
So you have to do it upon installation.
Yeah, and the amount of water will vary by the size of the trap, or if you're pretty crafty with it, I've seen people that will, if they know there's condensate in the line, they'll open a vent, or they'll leave it vented so that condensate builds up within. You don't have the outlet piped, so that you know some water is going in there first before it's going to have steam. But and again, the amount of prime is going to vary depending on the line size and things like that.
Okay. The next question we have is, we found that some inverted bucket traps do not have the small orifice. Why? And what happened if the orifice is closed? I don't completely understand.
Most of the ones I'm familiar with have that orifice, actually. I've not run into one that didn't have it. I can only make the assumption that with that particular model, they're just letting the steam condense within the bucket. I mean, it's still, yeah. So you've got the steam in there, and instead of it venting out and then condensing around it, and again, I'm making assumptions with this, but you're still, even if it's trapped in the bucket and you don't have that vent, it's going to condense. The trap should not be insulated, so if nothing else, the outside air should be cooling the trap, and that eventually any condensate in the bottom from the prime is going to help that steam condense in there. So making an assumption on there, because I've not seen that, but you're still going to end up having that steam condense, and the trap will open.
Okay, great. That's the last question we've got. So, Tim, thank you very much for your presentation. If anybody in the audience has any specific application questions, feel free to give us a call at 800-9-LESMAN or 800-953-7626. If you don't know your account manager, feel free to ask for me, Mike D. Lecluse, and I'll make sure that you get taken care of.
Yeah, and if this was helpful, I'm sorry, Mike, I didn't mean to interrupt you. I was just going to say that if this was helpful or you want it as a reference, it's not a proprietary PowerPoint. Send an email or call the Lesman folks. You're more than welcome to have a copy of this. It's no big deal. So if you want it as a reference, just let those folks know, and we'll send it along to you.
We are going to post this as a recording on our website, too, so it will be available in the next couple of days. Another question's come in. What steam trap works well at the end of a head steam line?
Of a what, Mike? I'm sorry.
It said at the end of a head steam line, so
a header?
I'm guessing at the end of a header.
Depending on the pressures, discs are decent. A bimetal is decent, and I see a fair amount of float and thermostatics too. But again, pressure-wise, as the pressures get higher, I see more of the disc traps and delta elements. So I'm thinking more like power plant type pressures where you're getting up into the hundreds, maybe 1,000, that type of thing. So it's going to be, again, there's no one technology for everything. So depending on the pressures in your main, that will vary. And in the main, the loads in a main are actually pretty small. That's one of the things I've run into out in the field a lot. People assume that because it's a large line that there's a lot of condensate being generated, but it's in a lot of cases not true. So you don't need a huge trap with a lot of capacity on those applications, because the mains are usually insulated, or hopefully insulated, and all you're doing is going out and then hitting distribution points, and you're not at equipment where you're heating anything at that point in time. So that's one of the fallacies, for lack of a better term, that I've run into several times. People think they need a gigantic trap on a steam main because it's 12 inches or something like that, and there's not a whole lot of condensate in many cases generated on a steam main. So you might have high pressure, but they can be small traps because the discharge volume is relatively small.
Good. That's the last question that I've received. Next month we're going to have a webinar. It will be held on May 23rd at 9 a.m. and it's going to be presented by Mike Cushing from Siemens. The topic is going to be how and when to properly apply chemical seals and remote seals to process transmitters. We will be sending out invitations to that shortly. At this point, if there are no further questions, our presentation will conclude, and we thank you very much for attending. But before we leave, we've got one more question. What is the amount of wasted energy for float disc traps?
Float or disc?
It just says for float disc traps. So,
okay, there two different technologies. Maybe you meant float and thermostatic. Those are pretty efficient. And I'll also mention disc as a separate one to make sure we cover the question. But float and thermostatics are actually pretty efficient. When they're operating right, you should not be getting waste out of those. They would normally, if the condensate flow stopped, they should close. And if they got hot enough, the thermostatic element will close. So they're very efficient traps. Disc traps will use about 2 pounds an hour of steam in operation. And again, that's brand independent. Ours do, anybody's does.
Okay. You answered his question because you responded back. Thank you.
Cool.
If there are any more questions, please feel free to type them in. If we have concluded the session and you do come up with a question, feel free to give me a call, and I'll get it on to Tim and get it answered. You can also email me, and my email address is very simply MikeD, M-I-K-E-D, @lesman.com. So if you have any questions, feel free to email me as well. At this point, we don't have any further questions, so we will conclude the session. Thank you very much for attending, And we will get a follow-up email out when it's posted to our website so that if you want to replay it or check back with some of these slides, you'll be able to. Thank you very much.
Thank you.